Let's integrate 1 over the square root of 4x squared plus 9 all raised to the power of 3 dx. Now the way to integrate this, which I find easiest, is through trig substitution. Because in my denominator I have the form x squared plus a squared. And I know when I have that, I could use the substitution that x is equal to a tan theta. The only thing that's different here is the coefficient attached to the x. So just to blow up what I have in that inner part of the denominator, this can be equal to 2x squared plus 9. And now this can be, or at least you could see this matching this form better now. So the coefficient of x in this case is 2 instead of 1, and that's the only main difference here. So knowing that, I know that I could define this using my tan substitution, so that 2x is equal to 3 tan theta. To isolate x, I'm just going to divide by 2 on both sides, so that x is equal to 3/2 tan theta. Now I could find dx, and dx is equal to just the derivative of that, so 3/2 secant squared theta d theta. Now that I have all my definitions, I could start plugging everything into my integral. So my integral is 1 over, and also I have the square root over something raised to a cube, so I could rewrite all of this to be 4x squared plus 9 to the power of 3/2. That's just the algebra of it all, because, square root is a power of 1/2. You multiply it by that 3, it gives you 3/2. Anyways, so rewriting this, my 2x squared, substituting that x in, I get that half is going to cancel with a 2, so that I'm left with 3 tan theta, all raised to the power of 2 plus 9, and all of this is to the power of 3/2. I'm mainly looking at this form because I think that's easiest to substitute in rather than this, but both ways work. It doesn't make a difference. Times my dx, which is 3/2 secant squared theta d theta. And now I'm going to be using, actually let's do more simplification. So this is going to be, I'm going to take that 3/2 out because it's just a constant. So 3/2, the integral of secant squared theta over, that is 9. Substituting, I'm distributing that square into that 3 tan theta, so that I have 9 tan squared theta plus 9 raised to the power of 3/2 d theta. Now I see that in my denominator, that inner part of my denominator, I have something familiar. And I'm going to use the Pythagorean identity that tan squared theta plus 1 is equal to secant squared theta. In my case, I have 9 tan squared theta plus 9 is going to be equal to just 9 multiplied by secant squared theta. The only difference between this identity and this one is the multiplication of 9, that factor of 9. So this is going to be equal to 3/2 again, not changing anything, just to simplify things, secant squared theta all over 9 secant squared theta to the power of 3/2 d theta. Now simplifying things, I will get that this is equal to, again leaving that 3/2 out, secant squared theta over, this will reduce, so it's kind of like you're doing a square root, and this will reduce to 3 secant theta to the power of 3. So I'm doing that in steps. And again, I'm also writing out a lot of steps that can be skipped if you're careful with your algebra, but I'm just writing it all out in case you don't directly see it. Plus, I like to write everything out just in case I forget something. So distributing that cubed in, and now I have 3/2 integral of secant squared theta. Distributing that cube, 3 cubed is equal to 27. Secant cubed theta d theta. I'm also going to take that 1 over 27 out of the integral because it's just a constant, and it will be, so I'll have 3/2 times 1 over 27. I know that that secant squared on top is going to cancel with 2 of my secants in the bottom, so I'm left with 1 over just 1 secant, theta d theta. These constants will simplify to 3, we'll go to 1 over 18. And then 1 over secant, we know secant is equal to 1 over cosine, so 1 over secant is just equal to cosine theta d theta. Now just integrating this, I get 1 over 18, because the integral of cosine theta is equal to sine theta. This is an indefinite integral, so I have to add a constant c. And now I'm almost done. I'm done with the integration. The very last step I have to do is substitute back my original variable, which was x. So going back to my definition, I said that x is equal to 3/2 tan theta, so let me write that over here. X is equal to 3/2 tan theta. And now I want to isolate that tan theta, so tan theta is equal to, dividing by 3/2 on both sides, it's going to be equal to 2x over 3. And I'm doing this because I know that tan theta is equal to the opposite over the hypotenuse of a triangle. So constructing a triangle, I could find the missing sides, and then I could, this ugly, I could find the missing sides and then find what sine is through the definition. So if that's the angle theta, my opposite is going to be equal to 2x, and my hypotenuse is equal to, oh, I'm sorry, that is not the definition of tangent, that's the definition of sine. It's opposite over adjacent, my bad. So if tan is equal to the opposite over adjacent, my opposite side is 2x, and my adjacent is equal to 3. And then using simple identity that a squared plus c squared is equal to c squared, I know that my hypotenuse is equal to 4x squared plus 9. And now sine theta is the one that's equal to the opposite over the hypotenuse. I got ahead of myself there. It's going to be equal to, let me make some space for myself. The opposite is 2x with respect to theta, and my hypotenuse is equal to 4x squared plus 9. Now that I have this all defined, all I have to do is just put everything back into my solution. So this is equal to 1 over 18 times 2x over the square root of 4x squared plus 9 plus c. And then that 2 will reduce that 1 over 18, so that this is equal to, and I'm also just going to combine this into one fraction, so that I'm left with x over 9 times the square root of 4x squared plus 9 plus the arbitrary constant c, and that is my solution. And that's it.